Hey, what's up, guys? It's Nick White. I do tech and coding stuff on Twitch and YouTube, and I'm doing something kind of different for this stream today. I thought it would be cool to make a YouTube video on what like some astrophysics kind of stuff. It's kind of computer science related, and it's what I did this past summer. So the LIGO, the Laser Interferometer Gravitational Wave Observatory, observes these gravitational waves that hit Earth from millions of light years away, from binary neutron stars merging and binary black hole mergers and stuff like that. And it's basically this data we can do like digital signal processing on and measure parameters and kind of come to conclusions about things in our solar system and universe and stuff like that. So that's kind of what I was working on over summer, but I only had a summer to do it, so I didn't really make that much progress. I'm going to keep working on it little by little. Maybe once a week I'll do a couple hours of a stream. But yeah, I just started this, so I'm doing the tutorial 0 software setup, where you basically just install these Python packages. I just installed all the Python packages, and then it gives this little thing before you verify software installation. You should have open up a Python file, and then we can run this Python file. It took a while to install this stuff. And then you can make sure that we can get our data working. So it just verifies that we have matplotlib, numpy, a couple other packages. So I installed all these, and then we're going to get going on this LIGO data, and I kind of want to test out a few things on the data. I think it's going to be pretty fun to do in streams over the next little bit here. So we're going to do an hour here and there. Let's see. So this tutorial 0 software setup, we just went through this. Probably pretty boring stuff that you guys don't want to see. Now we're in the data. Let's see. Getting started. Is that the end of it? Okay, getting started. Welcome to the Gravitational Wave Open Science Center. We provide access to LIGO and Virgo data. These are the interferometers that they have on. I think there's only 3 on that we have, 2 for LIGO and 1 for Virgo, that actually they use lasers to measure the gravitational waves, because they like pass through us, but they're super hard to measure. It's so I mean, I could explain how they work, but I'm not going to right now, maybe in a little bit. But as well as documentation, tutorial, and online tutorials for viewing data. So they have all the data of the gravitational waves. So the gravitational waves hit, and basically this laser uses light to kind of measure. It's like a displacement in light, I'm pretty sure. They have mirrors, and it bounces back and forth. A laser, and they're like 1 kilometer mile. It's like a laser 1 kilometer mile distance between the laser and a mirror, and the light goes back and forth. It bounces back and forth, and when the gravitational wave hits, it stretches and kind of bends matter. So when it stretches and bends the matter, the some like light gets released, and we measure the digital signal. We measure a signal based on the light that gets released there. I gotta kind of remember how it went. It was a long time ago. It's like 6 months ago, so I've got to refresh myself on this, but that's kind of how it works. And then we have the data from these, and we're gonna get deeper into it, and I'll remember how it works as we go through. But yeah, we're just getting started here. So provide access to so we have this data, documented tutorials, online tools for finding and viewing data. What are gravitational wave interferometers, general introduction, see the LIGO scientific collaboration, and Virgo. I kind of just explained it a little bit. Where's the data? The data page allows you to download LIGO and Virgo data. The main data time series samples are at 16,384 hertz or 4,096 hertz. Data is calibrated so that the gravitational wave signals have units of dimensionless strain. So delta L over L. I don't really know what dimensionless strain means, but how do I work with LIGO and Virgo data? With the tutorial page shows examples how to work with gravitational waves. You're a student, it's a great place to start. Software page provides links to an analysis software libraries used by LIGO, scientific collaboration, and Virgo collaboration. So let's go over this tutorial page. Each tutorial step-by-step through some common data analysis tasks, while GWOSC data can be analyzed using libraries in many software languages, C, C++, MATLAB. Most of these tutorials are in Python. We can see the software page for examples. We just downloaded all the stuff we needed. See the tutorial page setup for installing software to run these tutorials. We just did that. Tutorials shown here are not used to produce published results for gravitational wave software analysis package that are used LSC, Virgo. Okay, sure. So gravitational wave open data software web course 2018, self-paced web course on data analysis. We could look at that. Binary black hole events, use match filtering to find data signal noise. Okay, and then we have quick view notebook. So introduction to this. So what should we click here? What should we click? Introduction to data files, software setup. Did we just do that? Yeah, we just did this. Okay, so we can go to number 1, step 1. Download data. So browse available data sets, click on bulk data in the link in the menu bar. Here's bulk data. Available data sets are listed on this page. Timeline shows times of available data. Data for LIGO and Virgo detectors is only publicly available during times when detectors are operating under normal conditions. Okay, so we have the timeline, provide a convenient graphical tool for discovering times LIGO data was collected. Let's start by looking at the data timeline for H1 during LIGO's 5th science run. Okay, so yeah, I think they've only detected 7 or something, like 7 gravitational waves. It was like something like that. On the bulk data page, find the S5 data release, click on the timeline icon. So we have this. Clicking on this link, you should see plots like this. Here are some notes to understand the GWOSC timeline. The label on the far left indicates the instrument is represented in the plot. In this example, H1 count corresponds to the Hanford 1 detector. So there's different detectors. So I guess we have the detector that was used. Red curve shows the fraction of time data is available or the duty cycle in each time bin. So the y-axis goes from 0 to 100%. Okay. This data set spans LIGO's 5th science run from 2005 to 2008. Plot properties can be adjusted using the buttons at the top of the page or clicking on the section of the plot. Download data files from the data archive. Now we've got some idea when the data is available. Let's get actual data files. We'll try to find data for the month of S5 from November 1st to December 1st of 2005. We can query the S5 archive for the data we want. Click bulk data in the menu bar under S5 data release. Click the data icon. Okay. Use the radio buttons to select H1. In the web form, enter the dates, then click continue button. This will query the database for data files between the entered dates. You should see a list that looks like this. So we could do this in a second. Each line of the table corresponds to data file covering 4,096 seconds of calendar time. A given instrument may be up or down for a fraction of the time. Far right column shows what percentage of the 4,096 seconds contains the science mode data. Let's download one data file. We'll use this for the rest of the tutorial since we want a file with mostly scientific mode data. Let's download a file that starts GPS time. Okay, 815.411.200. So we're going to take this one. To download this file, just click on the link in the column under the heading HD5. So we can just download it right here, hopefully. Oh, great. Much easier than doing exactly what they said. So this is taking a minute. It's probably a lot of data. Use timeline to download data files. We can also use the timeline to find and download data. As an example, we'll download the same 4,096 seconds of data that starts from this, which is November 7th, 2005. It's very close to the beginning of the S5 run. Navigate to this, click on the plot, first month of 2005. So we have this, right? And you can use the buttons near the top of the page to zoom out if you make a mistake. Click on the link that says download this data, then click H1, link under get strain data. This should give you a list of data files. You can click what you want. Notice the data files are accessible through links with predictable names. It is also possible to write scripts to download multiple data files. What's next? Now that you have a LIGO data file on your computer, you can use Python packages to see what it is and make some plots. Okay. So we already have this file. Okay, yeah, so this was just showing you how to use the timeline to get this. So what's in a LIGO data file, guys? What is in a LIGO data file? Let's make sure we're still on. Okay, yeah. Well, what's in a LIGO data file? In this tutorial, we will use Python to read a LIGO data file. If If you do not have HD5 F5 LIGO data file stored on your computer somewhere, go back to tutorial step 1. If you do not have Python or some of the needed modules installed on your computer, go back to step 0, HDF5. I think I have that. I don't know if I got, oh no, I didn't get that. Windows users can skip this step. I mean, what do I need to do to get HDF5 though, guys? Yeah, so I don't have that. Okay, so we have to get this really quickly, even though my web browser isn't working very well. Let's go. Pick up the pace. Pick up the pace. Page not found. What? HDF5 for Python, sure. How do we download this? Install guide, HDF5, pip install. Oh no, I already have this. I have this. Okay, I did download this. Sorry, guys. So we can go back to whatever step was after this. Where were we? Tutorial 2. Okay. So yeah, here we go. If you don't have the HDF5, LIGO data, if you don't have Python or some of the needed modules, writing a Python script has two parts: the .py file, which is your code and should be created with a text editor such as Emacs or VI or Vim or Atom or whatever. If you installed Enthought Canopy, this should come with its own text editor, the Python interpreter that executes the code. To get started, try and open Python interpreter. This will be a little bit different on platforms. If you install Canopy, click on the Canopy icon, usually run applications. If you install Mac ports, yeah, sure. So similar, should work for Unix-like systems. You should see these lines. So we can just do this even though we don't have to. Python 3, there we go. We got the Python interpreter right here. Exit, and it exits. You can exit out of Python by typing this. Let's try a very simple program. Move into the directory where you place your LIGO data file. Now you should, let's just say LIGO stuff, right? So we'll have LIGO stuff, and then we'll put this data file in there, and then we'll put this AstroStream1 in there. All right, and we'll move into CD LIGO stuff. So we're in LIGO stuff right now. All right, there we go. We're in our LIGO stuff data directory, and let's try and write a very simple program. Move where you place your LIGO file. We're there. Now you should have open two windows at the same time: the Python interpreter window and a text editor window where you could see the contents of the new text file. We'll call plotstrain.py. Okay. So we'll do plotstrain.py. And I did I should do an underscore, so just because that's what they wanted. Plotstrain.py, screw it. Canopy shows both windows open by default. Just create a new file called this on this. All right, sure. So we'll just go into both the same directories. CD LIGO stuff, sure. And you know, it doesn't really matter what we do here, but we'll just do what they're saying anyway. Okay. So we're in it. We have this. We're editing it, and now we want to print "Hello World." Sure. Import plot strain. I don't know if I have this. And then save the file. Then in the Python interpreter, you can run the concept. Oh, okay. I didn't know that's how it worked. Okay. So vim plot strain, and we'll type print. We're using Python 3. Hello world. People who made this probably used Python 2. And then we'll save that file using vim. And then we'll do import plotstream.py. No module name. Oh, import plotstrain. Hello world. And there we go. So, or if you're using IPython, you can run the magic command instead. This is really elementary stuff that we're doing here. If all goes well, you should see text "Hello World" appear in your window. From this point forward, we'll assume you're comfortable with the basic features of Python. For a general introduction, we can go back to the tutorials, right? So let's try and read in and plot some LIGO data. In plot.strain, let's remove the code print hello world and replace it with this. All right. So now we're getting a little more serious here. So I'm going to use Atom. Vim is cool, but I just will do better if I do this. And this will tell Python that we want to use numerical Python, HDF5 libraries, and plotting modules. We'll always put this at the top of the script when we write the tutorial. Next, let's try reading the LIGO data we downloaded in the last step of this tutorial. So we'll just do this exact code that they're telling us to. Data file is now an object that can be treated as a Python dictionary. It contains all the information from the data file, right? So the data file is called, and we can actually do open add project folder, and let's just add LIGO stuff to Atom. We can remove project folder maybe right here. There we go. Now we have actually the stuff that we want here, and let's just get rid of this. We're using plotstrain.py, and then this is the name of the file, and it's very large, it says, so we're not going to want to open it, but we'll just do this and make sure that we actually have the correct name here, right? It looks like it was the same thing. So we take in this file here, and now we have access to that file, and we do data file h5py.file, file name r. So I'm guessing h5py is going to let us read this .hdf5 file because it's .hdf5. I'm not really sure about that format. It means something, I'm not sure, but F probably stands for file, D probably stands for data, and then H stands for something probably. Data file is now an object that can be treated as a Python dictionary. It contains all the information from the data file. To get an idea of what's in the file, add this code to plotstrain.py. So for key in data file.keys. So we're looping through the data file. We're going to print key. Try running this code in the interpreter. You can use the command import plotstrain, reload plotstrain, or if you have this, yeah, we don't have to do any of that. I'm pretty sure we can just do quit out of the interpreter and just say python 3 plotstrain.py. So print key is not working because this isn't the 1900s. No, I'm just kidding. We just wanted to we have to use Python 3 syntax. So for key in data file.keys, we print the key. We got meta quality strain, just like it says. This gives a high-level picture of what's contained in the LIGO data file. There's 3 types of information. So we have a metadata for the file, basic information such as the GPS times covered, which instrument, etc. Quality refers to the data quality. Main item here is a 1 Hz times HC's time series describing the data quality for each second of data. This is an important topic. We'll devote a whole step of the tutorial working with data quality information. Okay. Strain data from the interferometer. In some cases, the data, in some sense, this is the data, the main measurement performed by LIGO. Okay, strain. For a general introduction of gravitational waves and measurements made by LIGO, we suggest reading articles and watching videos. We don't need to do that. Plot a time series. Let's continue by adding to plotstrain.py to make a plot of a few seconds of LIGO data. To store the strain data in the convenient place, add these lines. So it's literally just telling us exactly what to write. I don't even think we need these lines anymore. So strain is data file strain. So this is a dictionary of this file's data, and we're accessing the strain key, and then we're getting the value of that strain object. And then we have time series, I guess, is equal to data file strain dot attributes of XS spacing. Not really sure. Code. The code above accesses the strain data object that lives inside of the group strain, so it's a group strain. The attribute X spacing tells how much time there is between each sample. And we store this as a TS. The value of the data object contains strain value at each sample. We store this in strain. See all the structures of a GWOSC data file. We'll look at the view a file tutorial. View a file tutorial. Yeah, we can just look at it. So this is the structure of the file, kind of. use HDF view, a helpful free software for viewing the HDF file in the HDF view tool, which can be downloaded on the group site. This will give you access. Alternatively, you can write short Python script for viewing the structure. Okay, so we have a dump info. Import HDF5, visit items, dump info. This is kind of what it looks like, I guess. So meta, time series data from GWSC, just metadata, and then we have quality data. I mean, this is just kind of what it looks like, I guess. And then we have attributes. This is what we're getting the X spacing. This is the time between something. I forgot already. All right, cool. That's what it looks like, I guess. Where were we then? We are down here, right? So to calculate how much time passed between samples, okay, yeah, we're right here. How much time there is between each sample as we store this as TS, value data object, view 12. Now we can, let's use the metadata to make a vector that will label the timestamp of each sample. In the same way that we index the data file as a Python dictionary, we can also index data file meta to see what metadata we have to work with and add these lines to plot strain.py. So we'll print out some metadata, print \n meta keys equals data file of meta.keys. So we're printing out metadata here. For key and meta keys, print key, meta key.value. So we're printing out the key of the metadata and the value of the metadata. I mean, all right. Let's do it. Print key, meta key.value. So we'll do print key, print meta of key.val. .value or .val? .value. Okay. And then we'll call this again on this. You can't do this. Yeah, we have to update all this crap just because they're using Python 2. I mean, it's kind of annoying, but Python 2 is going to be deprecated soon. So, okay, so that worked. Syntax error, missing parentheses, and call to print. Did he mean print this? Yeah. Description, so strain time series data. So this gives a description of the metadata key. So strain time series data from LIGO. So can we actually just do this? Because I don't even know what the key is. And then we'll do value here. I think that'll help. We don't need the operating systems textbook right now. Okay, key is description, and then we have time series data from LIGO, key description URL, and then we have the URL, then we have detector, H1, duration. So each file has a bunch of metadata, and then we have GPS start, you have a starting value, observatory. So yeah, we have a lot of good metadata, it looks like. So that's just showing us the metadata we have to work with. That's going to be useful, I guess. In the Python interpreter, we can enter reload plot strain to see the output of this. You should see that GPS start time and the duration are both stored as metadata. To calculate how much time passes between samples, we can divide the total duration by the number of samples. Okay, and it lets us just gives us the answer for this. To do that, so we have GPS start. We grab the metadata GPS start value. We have the whole duration here, and then we have GPS end, and then time equals numpy.arrange GPS, and then we could probably just print time. So the numpy command arrange creates an array. Think a column numbers that starts at GPS start and ends at GPS end, and has an increment of time series between each element. Increment of time series between each element. Okay. Time series is set to data file strain of X spacing because that gives us the distance between each sample. The time distance between each sample from earlier. I forgot about that. Finally, let's use all of this to plot a few seconds worth of data. Since this data is sampled at 4096 Hertz, 10,000 samples corresponds to about 2.4 seconds. Sure, and add the following to plot strain.py. This looks all fine still. Number of samples is 10,000. We go from time 0, num samples, strain. Time is, where's time? Time is right here. Time is a plot kind of. And strain is up here. The strain value, okay. GPS time, H1 strain. And then we could run this. Okay, here it is, great. So this is some LIGO data. We have the H1 strain and the GPS time on the x-axis, H1 strain on the y-axis, and it's from -1 to 1, it looks like. And then we have the x sample is the time between each, I forget, but I don't know. It's like the time between each sample. So I still don't really know what this data looks like exactly. It must be a ton of, I think it's a ton of like points. It's got to be a ton of points in columns. And this is 10,000 samples, all split up by, it's like 0.002 seconds each or something like that. Yeah, like if this is 10,000 samples, then the x spacing was like between each individual sample, the time, and it's like 0.002 seconds or something like that. So this is just plotting from time 0 to the ending time, or I don't know what strain. Oh, from time 0. Nope, still don't. I'm not 100% sure what this is, but I don't. It's just a tutorial, so it's fine. We're just kind of seeing what the data, how the data works a little bit. We'll get better as we go along. Anyway, the last command, plot.show, may not be necessary if you're working with matplotlib. Interactive mode, you can turn interactive mode with the command plot.ion. Now in the interpreter window, type reload plot strain or run plot strain. You should see a plot that looks like this. We did that. You may be surprised how the data looks smooth and curvy, rather jaggy and jumpy as you might expect for white noise. That's because white noise roughly equal power at all frequencies, which LIGO data does not. Rather, LIGO data includes noise that is a strong function of frequency. We often say that noise is colored and distinguished from the white noise. The wiggles you see in the plot above are the low end of the LIGO band. In general, the LIGO noise is dominated by these low frequencies, so it's more dominated by low frequencies, I guess. To learn more about LIGO noise as a function of frequency, take a look at the plot gallery. Okay. Yeah, low frequencies, it said. What's next? You may want to see the whole structure of LIGO data file. This doesn't really show me the whole structure of LIGO data though. It just shows all the data that we can get from this kind of object. So it gives us the x, obviously we know what's important now. The distance between each sample, the number of samples, the starting GPS time point, the ending, just all that crap. I know how to plot it now, so that's fine. Okay, working with data quality. In this tutorial, we take a look at how data quality information is stored in LIGO data files. If you're not comfortable with using Python to read a LIGO data file, you might want to take a look at step 2. We just did that. What is data quality? Understanding data quality is important when working with LIGO data. Before performing any analysis, you use this tutorial in the data documentation to identify the appropriate times for your analysis. Times which fail at the data category flag are represented by nans and should never be analyzed. Okay, so if it fails at the data category flag, don't analyze it. Okay. Quality is really important. Okay. Times which fail at any CAT1 level flags are severe problems and should not be searched for in astrophysical sources. Okay. In addition to the main data output of the LIGO detectors, the strain channel, there are hundreds of other data file channels that are recorded to monitor both the instruments and the external environment. Some of these auxiliary channels are used to create data quality flags to note times when the strain data is likely to be corrupted by instrumental artifacts. The data quality flags are organized into categories by how severe of an impact they might have on a given search. Okay. The categories for each type of search are defined differently, but in general, a lower data quality category indicates a more severe problem. So, for example, in CBC low, category 1 means that structured data is strongly corrupted. So, if it's CBC low, category 1, strongly corrupted and cannot be used to search for low mass compact binary coalescence signals, but a CBC low category 4 flag is a less significant problem in the data. Okay, so flags will tell us if there's problems with the data quality, and if it's a really low one, then it's bad and we shouldn't use it or analyze it, but a higher one is less important. For more detailed explanation, the meaning of various flags, see the data documentation. How is data quality information stored? Data quality information is stored in LIGO data files as 1 Hz time series for each category. Notice that different sampling rate than the 4096 Hz rate, which is used to store the strain data. So, for example, the first sample in the data quality channel applies to the first 4096 samples in the corresponding strain channel. In the S5 dataset, there are 18 quality categories as well as 5 injection categories. Each represent a 1 Hz time series. Let's print out the S5 data quality channel names from the LIGO data file. In the same directory where the data file you downloaded step 1, create a file named dq.py. Let's do it. Let's just do everything that they say. No questions asked. Terminal's not working right now. There we go. Alright. Let's create a new file. What is it called? dq.py. There we go. We got dq.py. Let's grab all this because it looks like we need it. Place the following code into it. Great. Try running the code in the Python interpreter. Obviously, we have to switch some stuff. So bits, bit name list, bits. So bits, bit name list of bits. Is that all it was? I forget already. I think we can run it now. Okay, great. If you're using this, import DQ and reload DQ. If you're not, you should see data quality names. For explanation of each category, see the dataset documentation. Okay, so we have a file name, we have a data file, same thing as we did last time. We have a GPS start time. DQ info is the quality data file of quality simple. Bit name list, DQ info, DQ short names dot value, n bits equals length of bit name list for bit in range of n bits, print bit name list. Okay, so bit name list is, so we go to DQ short names dot value. Okay, so we have data, C high, all this crap. Use data set instead, H5Pi deprecation warning. Okay. This is interesting, very interesting stuff. Sure, dude, sure. And we can look at what all this stuff means if we want to. Dataset documentation. Well, we're not going to look at that right now, apparently. All of the data quality categories are combined into a bit mask and stored in an array with 4096 entries, 1 entry for each second of data, and the LIGO data file is called the DQ mask, and you can extract it from LIGO by adding this code to dq.py, so we get this Q mask. Okay, sure. Each sample in this bit mask encodes all 18 data quality categories as a different digit in a binary number. A one particular digit means corresponding flag is passed, so the data is good at that category level, and a 0 means the flag is off, so the data is bad at that category level. For example, DQ mask means a value this in S5 data would mean that the detector data is available data in that it passes the whatever criteria but fails all of the other quality conditions. So it passes these flags, fails everything else. This is a compact way to store a lot of information, so it stores it as a binary number. Zeros are bad, ones are good. This is a compact way to store information, but to work with data quality, we want to put things more convenient for them. Let's try and unpack some of this data quality information. In most cases, you'll not want to keep track of every data quality category, but only a few values that are important for your search. For example, to search transient gravitational wave sources such as supernova or compact object mergers, you may want to keep track of a data category along with burst categories. As an example, let's try unpacking the burst cat 1 and data categories. Try adding dq to .pi. So we add this. It didn't even say to do this, so let's see. Now the variable psi will be 0 everywhere the data fails at the data category and 1 everywhere the data passes the data category. Similar, burst cat will be stored in a bit. In bit 9 and burst 1 variable will correspond to this category. In a typical case, you only want to use data where all the categories of interest are passed, signaling relatively clean data. To accomplish this, just take the logical element Y's and all the channels you need. Okay. So, oh, and we need QMask still, so I was wrong. We shouldn't have deleted that. Yeah, so what we want to do is we want to get all of these data categories, and we're basically, whenever we actually work with data in the future, we're going to go back here and check on these things and make sure that the data is good to use. I mean, just data quality stuff, and we just look at it here, it kind of explains it anyway, so we'll be able to figure that out later. They have good explanations. I like these tutorials, pretty good. And then we have good data 1. Okay. To confirm good data 1 is on when both the data and burst cat 1 categories are passed, we can make a plot of these 3 channels. You can literally plot them nice. We don't even need to do this right now. We can just do this. Let's see what happens. We have a deprecation warning, so we have to use data set instead. Instead of what? Dataset.value has been deprecated. Use dataset instead. Like, what do you mean dataset.value has been deprecated? So we just delete these. Unsupported operand types for dataset and int. Well, we need the values. So how do we get the values? Use dataset instead. So what is it, like this? I don't think that's what they want. No. Huh. What do they want then? I don't know what they're saying really. They're saying use dataset indices. We're using the indices, and then they're putting. I don't know what this means. Let's look it up. Like, what does this mean? You have to post the full stack trace. Code, yes, the code seems to be working. What? This is merge, some merge thing. NumPy array.fill value, dataset.py. I mean, I don't know what this wants. Okay, nobody will help. I don't know what they want though. Oh God, I don't know what they want. Like, use this and no, I don't want it to, I didn't make it callable. Like, what do you mean? Dataset.value has been deprecated. Use this instead. Yeah, what does that mean though? I don't know what they want me to use instead. You can't use .value, but what do you put? Property dumps the entire dataset in NumPy array. Using code.value should be updated to use to NumPy indexing using my dataset of this as appropriate. Okay. But if I just delete these, you would think that you would just delete them. Okay, maybe you do just delete them and it's fine. But you can't use unsupported operand types for dataset and int. But it wants like a value, you know? GPS start is meta of GPS start. You would think that works and that gets the value. Can I print GPS start? Python 2 problems. Oh, the errors before. GPS start, what am I printing? I'm printing a data set. I don't want the data set, I want the value. So how do we print the... This is annoying. So we have to go back. How are we printing these earlier? We were doing, what is this, step 2? We're in step 2, right? Step 2 was letting us print this stuff, .keys. It was saying that .value is fine earlier. I hate this. .value, right? Let's try this. So yeah, that's what we want. We want the .value, but you shouldn't, it's saying you shouldn't use that. .value deprecated Python. Dictionary .value Python. Yeah, how do you dict.values? I mean, what do you, like, get the value, I want the value. Yeah, this is what it says to do, but what? Okay, let's go back and try and print all of these, honestly. Alright, let me see. For key and data.files.key. Okay, we have all of this. So then you go into meta of GPS start. How do we print the metadata? Dot attributes. Data file meta dot keys. So we have to use dot keys or something. Key meta keys of key. Wait, no, meta of key. Okay, yeah, so we want the value of these. Dot value, and then if you use dot value, it works. Meta of key dot value, like what? Get value of object Python. Yeah. Dot value. Get 3, Python 3. Okay, let's say dot keys. It doesn't have that. Oh my god. Alright. Howdy, Red Bread Redemption. How you doing, dude? What's up, man? I'm having a tough time here. H5 by deprecation warning. It's not letting me use value. Yeah, what is this? I'm not getting any help here because nobody uses these files. Okay. Yeah, literally nobody uses these. So it's tough to get an answer here. Yeah, I mean, it says you can ignore it since it still works, I guess. So we can just delete it. I mean, we're just gonna use the dot value thing. I mean, since they use it. It's just not letting us use these though. I don't know. So let's just get back into what we were doing here. Try dir object. It'll split out available attributes. I could try that really quick. You're saying with so GPS start. Let me show you what GPS start does. Should work. Yeah, so let's delete these. Let me show you GPS start. Where is that? Yeah, so instead of an H5 dataset, it should be an integer. I want the value of GPS start, so I'm going to try what you said. So here it is. Here's all the attributes, like you said. It should have a value attribute, right? Because that's what I'm using. Yeah, value. What I want is the value. But it's when I do dot value, so because what I want to use is GPS start dot value to get the integer value. It's saying that's deprecated. It's saying that to use this instead. I mean, I don't really know. Does it mean this? GPS start, GPS, yeah, that didn't work. I mean, I don't, yeah, it's not working, so I don't, know what they want me to write. You know, I literally have no idea. Do they want this? Like, what do they want from me here? You know, that doesn't work either. So I'm just going to keep using the dot value attribute because I don't know why they have it says deprecated, but there's no other way to get the value from what I'm seeing. Let's see. Dataset object not callable. GPS start. Here it is. Yeah, one sec. Hello?
Did you get a W-2 from your college that you did your internship at?
No, I'll get that like after this.
Okay, and you can get it off the computer?
Yep.
Okay, and then just bring it down. Thank you.
All right. Sorry, I have to do my taxes, so I have to get my summer research information for my taxes. But all right, that's fine. So that's all set. Let's just continue. I'm going to use dot value for all of it. I don't really see the problem with using dot value. I don't really see how we can do it any other way without using dot value. So we're going to use dot value here. I don't know why these aren't working either. This tutorial is kind of falling apart here. As an example, let's try unpacking these. I'm just putting everything that they're telling us to write here. We don't need the bit names anymore, and if we run this, yeah, we can't use this. Unsupported types, so it's saying that this is bad. Unsupported types for dataset and int, because QMask is it not unpacking the value of QMask? Let's try printing QMask. Like, it's becoming a problem, actually. QMask, to like do these tutorials, it's becoming a problem. QMask is an array. I mean, that looks fine to me. What do they want? Maybe it's data sets to extract values. I'm a little out of context. That's not pure Python thing, but that should still work. I mean, let's see. Maybe you're right. So you're saying to do this? I guess that's a weird thing. Index error. Only integers, slices, ellipses. Oh, you're saying that I have to write this? What the hell? Data set? I don't know about this one. Like this? Maybe. Yeah, data set's not defined. Yeah, that doesn't seem right. Yeah, that's not like a... Yeah, that was a good try, but I don't know, dude. It's just like... I don't think... Oh, you think dataset is a type in NumPy? NumPy.dataset? NP I have it as. So maybe if I do this... Yeah, I don't think so. It's just nothing, dude. So, unfortunately, I don't know what's going on here with this dot value thing. It looks fine. It looks like it's getting the value fine. But it's saying QMask, NumPy dataset of QMask. Yeah, so it's just, it looks like it's getting the value fine. It looks like, I don't know why this plot isn't working then. Let's see. Deprecation, that's it. That's all it says. I feel like they're saying this, but that's not going to work. And they're not saying this. Are they? Wrapper. Field names only allow for contact types. Maybe that worked. Line 13. No, it didn't work. Alright, we're going to have to move along in this tutorial. I'm not going to spend all this time on it. Terrible deprecation message, I guess. Yeah, I don't know what this is even saying to do, dude. Honestly, we're going to have to skip this part. Here are some things I noticed on the plot. Channels are offset. This is just data quality right now, so we'll have to worry about this in a little bit here. So let's just go to step 4. This tutorial picks up where step 3 left off. Step 3. Okay, I actually have to do this tax thing, so I'm going to do another stream on this in a little bit. This is the first of a series, so we got through step 1 through 3, even though we had complications at the end. Maybe I'll look into this in a little bit and figure out how this works, but I have to get my taxes done, and I have to do a couple other things. I have to finish I have a physics homework assignment due at 5, so I'm going to finish that really quick, and then finish physics, get the taxes, and then I'm going to stream again for another hour or so, try and get through all these tutorials, and yeah, that was the first one, so thanks to anyone who watched this. It was pretty boring. We're just kind of going over the tutorials here, but in a few weeks, or maybe 10 weeks or something, we're obviously going to get pretty far into this, so stay tuned for that. I'm going to be posting these on YouTube, so let me know what you guys think about LIGO, and if anyone else is going through this. I think it's a pretty cool topic to get deep into, and I want to get good at digital signal processing, so let me know what you guys think, and I'll see you guys later.